This is CPM Calculus, Chapter 4, number 100. So the graph to the right shows the velocity in miles per hour of a car during a road trip. So here's the graph. The y-axis is velocity, and the x-axis is time, right? Velocity is in miles per hour. I'm going to write that on the graph. And time, we have hours, right? This is time. All right. At time 0, t equals 0, the car was on the Golden Gate Bridge heading north. Okay. So part A says find the function for v of t. So here's v of t. It goes down here. It looks pretty linear, right? It curves a little bit and goes up. All right. So we don't really have a specific curve that does this in mind, right? It's not like we have memorized specific curves, but what we can see is that there is a linear shape here, right? And then a linear shape right here, okay? And those kind of meet like right around, I don't know, around here. Okay, so let me go ahead and draw that in blue. Like we have a linear shape here. I'm trying to make it go over the line. And one here, right? Because our goal isn't to get exactly this function right now. It's just to kind of find a function for v of t. So what I see is two lines that meet here at, if this is t is 0, 1, 2, 3, 4, 4.5, right? They meet here and they're two different lines. So how I would describe this function v of t is going to be a piecewise defined function, right? You have one line until 4.5 and then another line after. So let's go ahead and do that. So I have one line until, for t is between 0 and 4.5. So 0 is less than or equal to t is less than or equal to 4.5. And another line for when t is greater than or equal to 4.5. Or let's, because we can't have both points be described by, we can't have the point t equals 4.5 described by both pieces, so I'm going to just say this was t is greater than 4.5, not greater than or equal. Okay, so now we got to ask ourselves, what's the equation of this line, right? Well, this line right here, right, it has a slope of, it goes down 20, right, if this is up 10. So it goes down 20 every time it goes right 3. So the slope, so the equation is a line, so I'm going to say y equals mx plus b. The slope I'm saying is down 20, right 3. So that's the change in y over the change in x, right? Oops. So that's going to be down 20, negative 20 over 3 x plus b. The y-intercept, it hits our our y-axis here at y is 20. So the y-intercept is 20. Okay? But since we have it in terms of t and not x, I'm going to go ahead and say negative 20 over 3t plus 20. Okay, that's the line right here. And then going from 4.5 into the right, I'm assuming that it keeps going up. Maybe we should just stop it at 6. But let's go ahead and leave it. Oops, I deleted the 0. Leave it as greater than 4.5. And like any line, we can go ahead and find out where the y-intercept and what the slope is. Or we can pick 2 points. Right? I'm going to pick these 2 points here. This point 5, 0, and this point 6, 2. No, 6, 20. Right? This is 6, 20, and this point is 5, 0. And I'm going to use those 2 points to get the equation of the line. Right? I have 6, 20, and 5, 0. Then I can use the equation y minus y1, point slope form, equals to m times x minus x1. Okay? I'm going to use this point. So it's y minus y1 is 0. The slope is the change in y over the change in x. So the y value goes from 20 to 0, so 20 minus 0 over 6 minus 1. 6 minus 5, excuse me, times x minus, here the x value is 5. Alright, so that's y is equal to 20 minus 0 over 1 is 20 times x minus 5, which is just 20x minus 100, right? So if I'm going to put that here in terms of t, I'm going to say 20t minus 100. Okay? So that's how I'm going to define v of t. Okay, so this is part A. Right? Part B then asks, how far north has the car traveled in 3 hours? So this is asking about how far, and that means distance, right? And that's okay for us because even though this graph is velocity versus time, we know that the distance is going to be the area under the curve, under the velocity curve, right? And even better is we can get this without doing any like integration, because we can see that this shape here, right, from 0 to 3 is a triangle, right? We see it's a triangle. So the distance at 3 hours, I can go ahead and write this as an integral. Well, I'm not going to because we're going to do that in part D. So the distance, we know it is just the area from 0 to 3. This is part, the first part, because we're asked at 3 hours and at 4 hours. So at t is equal to 3, distance is equal to the area from 0 to 3. And that's just 1/2 base times height of this triangle, right? The base is 3 units, so 1/2, 3. The height is 20 units, so 1/2, 3 times 20. And that is going to be 30. And what are the units? Well, the y-axis is miles per hour and the x-axis is hours. So that's 30 miles per hour times hours, or these cancel out, it's just 30 miles. Okay? So in 3 hours, the car has traveled 30 miles north. I can even write north next to it to give direction. At 4 hours, right, the distance north. So again, this is distance north. We have to take into account this region right here, right? It has gone, the velocity is negative here. So it seems like we're traveling south now for this region, right? So the distance at t is equal to 4 is equal to the area of this triangle minus the area of this triangle, right? So we can go ahead, we know the area of this triangle here. So we know it's the area from 0 to 3 minus the area from 3 to 4, right? That region right there, minus the area from 3 to 4. And I'm writing it like this because we're kind of familiar with writing the boundaries like that, and this represents from something to something. All right, so the area from 0 to 3 we know is 30 miles, minus the area from 4 to 3, again, is a rectangle. 1/2, the base here is 1 unit, right? So 1 hour. The height here is basically when we plug in 4 into the equation, we're going to get the height of, well, 4 into t makes that negative 20 over 3 times 4 plus 20, right? So that is the area of the second triangle. I'm going to add it because I already put a negative 20 right there, because the negative 20 represents the negative value down here. Okay? So what we can do now is I'm going to use a calculator really quick. So I have 30 plus 1/2. Oh, I'm just going to say plus 0.5, same thing as half, times 1. I don't even need to write that because times 1 doesn't change it. And then times, in parentheses, I'm going to put negative 20 over 3 times 4 plus 20. And I need to put it in parentheses here because this is going to be distributed into both of these terms. Okay? So I go ahead and do that, and I get 26.667 miles again north. Okay, so that's how much it traveled north, right? Because we head north, the car is traveling north, and then negative speed, it's going south. Here it stops. So it seems like it's traveling somewhere really fast, slowing down, stopping, and then going backwards or turning around. Okay. So now we could go on to C. Oh, so this is kind of what I just said. Explain what happened to the car between the 3rd and 5th hour. Okay. So it looks like the car, since the velocity got negative in the north direction, the car actually was heading south, right? So he turned around or went backwards, and that's what's happening. So let's just write that. Between 3 and 5, we know velocity is negative between I'm abbreviating BTWN, between 3 and 5 hours. And that's the same thing as speed in the south direction, right? And why do I say south? Because remember at the beginning, this graph is showing the velocity traveling north, right? And velocity is just, remember, a vector versus magnitude is speed, right? Speed has magnitude, velocity has magnitude and direction. So speed in the south direction is the negative velocity. Okay, so part D says to set up an integral to represent the displacement from 0 to 5. Okay, so the key word here is displacement. Okay, because we're going to see in part E the same thing, set up an integral to represent the total distance from 0 to x. So displacement is basically, if you start here, you go up, you go down, you end here. Well, displacement would be the distance between your start and ending point, while the total distance traveled would be the total distance to this point plus the total distance to this point, because it's all you're traveling no matter what direction you're going in. Okay? So, setting up an integral to measure displacement is basically going to be the integral, right? If we look at our graph, from 0 to 5, it's saying, right? Yes, from 0 to 5, it's the area under the curve is our total displacement, right? That's our distance, and we want to include if we're going back, right? Just like we did in part B, we subtracted this area because it was negative speed, meaning distance was going backwards, right? Because we were asked how far north it was traveling, and it was going south from 3 to 4. So here we want to go ahead and set up the integral. Well, what's our function? Remember, our function is just v of t, right? Our function is v of t. And so to set up an integral, we're taking the integral with respect to t. So we write the integral of vt dt. And we're going from 0 to 5. So then we just put the boundaries 0 to 5 here. Okay? So this part is pretty straightforward. Part E is a little bit more difficult. Because E, we have to think about the total distance, meaning when we're looking at the area, when it's negative, we don't want it to be negative, we want it to be considered positive. So how do you get the positive section out of a negative section in a graph? Well, that's where we take the absolute value into play. Because if we take the absolute value of Vt, right, and then take the integral of that from 0 to 5, the absolute value is just going to be the graph above the x-axis, or the t-axis here. So it's actually going to be exactly what we want. It's going to represent the area here in green, and it's all going to be positive, right? Because we're going to take the absolute value, so any negative value is going to be flipped up above the axis. So in part E, we're going to take the absolute value. I'm going to make it darker, and that's going to give us the total distance traveled regardless of direction. Alright, so there we have CPM Calculus Chapter 4, number 100.